So welcome to the next lecture. I'm Christof Monz. I'm heading the language technology lab here. And my background is in NLP. I also used to do IR a long time ago, 20 years ago or so. But for the last 20 years, I'm mostly doing multilingual NLP with quite an emphasis on machine translation. And of course, also these days, neural machine translation. And of course, a lot of that work these days is around transformers. Now, so what I want to do in this lecture is really just give a bit of a foundational overview of transformer models in, let me just see, with the different flavors that we have. And so I'm going to start actually with a sequence-to-sequence model, which is nowadays mostly like in the, say, more commercial models like the Geminis or the ChatGPTs are decoder-only models, but I want to start actually with a sequence-to-sequence model, an encoder-decoder architecture. And then later on, that will be the bulk of this lecture, then later on also focus a little bit on the encoder-only model, and then also say a little bit, a few words, how this relates to a decoder-only model. So in a way, you could really treat a decoder-only model as a simplification of an encoder-decoder model, or sequence-to-sequence model. I want to talk a bit about architecture in general, but also about the attention mechanism and also beam decoding. So how do we use these models actually in inference time? Beam decoding, by the way, is fairly architecture independent. So I'm going to talk about beam decoding even before I talk about transformer models, because it doesn't really matter whether you use a transformer model or whether you use a CNN-based or an RNN kind of family-based model. Then about the transformer model, a bit more the internals of the model, the layout components, the position encodings, but also how we train these models, because there are some things actually one has to be a bit careful about when training these. And then I want to segue into contextualized word representation. So now we're going back from, let's say, using these models really directly for an end-to-end task, but also using them, for instance, in a kind of pre-training, fine-tuning setup. And then also look into an encoder-only model like BERT, and also how we can do pre-training, which also, depending on the learning objective, it's much easier to scale much larger data sets for an encoder-decoder setting like Monz architecture. All right. So at the very beginning, so I'm not going to talk in just one or two slides about language modeling in general. So it's actually, yeah.
I think people at the back are not hearing you well. Can you move the mic?
I can move it again. You could also come further to the front. Is it better now? Yeah, you have to say something, otherwise I don't know. Yeah, okay, all right, okay. So language modeling in a nutshell. So it's actually worthwhile to remember what language modeling was meant to do, because they're not parallels in which we use it today. So the original task of a language model was to estimate the probability of a sequence of words or a sequence of tokens. And why do we want to do this? Of course, we can do this sequence as a whole, which becomes computationally basically a bit complicated because we just data sparses issues. So typically what we do is we reformulate that into predicting the next word given a history. And again, the olden days, the history also had severe limitations in terms of data sparseness. Nowadays, with neural models, that becomes actually much easier to generalize to much larger histories. But anyway, so the point here is that we want to estimate the probability of a sequence. And we wanted to do this for actual tasks. So language modeling, since its beginning, was always a very general task. It in itself was not very useful for something, but we also used it for tasks, the actual end-to-end tasks, where a language model can provide some useful information. So for instance, machine translation is one of those end-to-end tasks. And so why is it useful? Because these language models, they do estimate or an approximation of syntactic fluency. So how well formed is a sentence, how grammatical is a sentence, but also how semantically appropriate is it, right? I can have a sentence that is grammatically fine, correct, but doesn't really make any sense. And also like general well-formedness. That's really difficult to pinpoint what we really mean by this, but you could sometimes get the feeling, yeah, well, it makes sense, but it feels a bit off, right? So by just measuring the probability of a sequence, we get a fairly good approximation of all of these characteristics, which are, of course, desirable if you want to produce human-like output. And in the olden days, these models were really used as a component. So the language models were used as a component in another end-to-end task. So for instance, speech recognition. This is now a bit of a cartoon example here. But for instance, when I have a sequence like audio signal comes in and we want to do a transcription of this, like we want I scream versus we want I scream, then you want that the second sequence has a higher probability. Therefore, that's what is returned by a speech recognizer. In machine translation, we don't really have those kind of errors. We have different types of errors. We have word reordering errors like get, we, I scream. Of course, we have a lower probability than we want I scream, right? So that's what these language models were used for. So back then, they also had a very general purpose. In themselves, they were not so useful, but they were used in combination with other models. And of course, that's also how we use language models, large language models these days, right? Then by themselves, they're actually not so useful, but we train them for specific tasks, a huge variety of tasks, and now they become useful. And so in today's lecture, I really want to focus on the initial phase, like the pre-training phase. Like, what do these models look like? So the model that I want to start off with is a sequence-to-sequence model. So in sequence models, or not sequence-to-sequence, so sequence models in general is what typically we have in NLP, right? Because we have a sequence of words, so typically an audio signal even. And you can think of sequence models that assign a class to an entire sequence, so classification task, think of sentiment analysis. It can also assign a class to each element in the sequence. So this is more like a tagging task, entity recognition, for instance, or part of speech tagging, these kind of things. Whereas in sequence to sequence, it's different. So we basically input is a sequence and output is also sequence, but it can be of different names. Right? That's different from let's say, the labeling task in where we have each element in the sequence that assigns a label, is assigned a label. And so whereas the sequence labeling assumes a one-to-one mapping, so each input symbol is given a class, this of course not the case for sequence to sequence, right? The input can differ in length from the output. And these mappings between the input and output, which can be fairly complex mapping, have to be learned through training. So we also have this a supervised task, so it's not a self-supervised task for sequence to sequence. And so in the next few examples, I focus a little bit on machine translation. We're not going into details of machine translation, but it's one of those prototypical sequence-to-sequence modeling tasks. I think I also have a list of other tasks that I want to mention, like summarization, right? A document comes in, produce a summary, obviously of different length. Dialogue systems, bit of a question mark whether that's really a sequence-to-sequence task, but another story. So input is a question and output is a reply sequence. Machine translation, input is a foreign sentence, output is a sentence in the language the user speaks. I had more examples, I think. Okay, I cut that slide. And so in order to train these models, so summarization or dialogue, we also need some data, right? So for summarization, we need an original document, we need a summary. And for machine translation, we need an input sentence in a foreign language and output sentence in the target language. And here's such an example, right? So here I now have Chinese English. We call this a parallel corpus. And basically from this corpus, everything that's on the left, that's in Chinese, that's digested by the encoder, and everything that's on the right is treated by the decoder. This is basically designed out of the sequence. And of course, we do this. This is the only annotation we give, right? We don't say which words correspond to which words. So the model figures that out by itself. So here, for instance, I see like these three Chinese characters tend to co-occur with Singapore, or maybe also Singaporean, something like that. And so probably they mean Singapore, right? And that's what the model basically looks. It just observes these sequences, and through co-occurrence statistics, it learns a mapping between the input and the output. So that later on at inference time, when we only present it with the Chinese input, it can generate in English output sequence. Now, for the general encoder-decoder architecture, we have a complex input that needs to be encoded into a representation. So that's the difference from decoder-only models, is that we now really get an input sequence, we digest it as a whole, and give a representation for that. That can be a single representation, can be also a sequence of representations. We come back to that later on and talk about attention. And of course, also a complex output. So it's not just a label, but an entire sequence that we now want to generate given this complex input. And so there are many tasks. Also here other tasks actually in addition to summarization. So for instance, you can also think of image capturing as an encoder-decoder, not so much a sequence-to-sequence task. So image capturing, the input is an image, right? That you, for instance, analyze CNN or your architecture of choice. And then the output is a description of this image. Again, you have to learn this from data. So you need image annotated data, with caption annotated data. Speech recognition, right? The input is an audio signal. And here, again, you want to output a transcription of this in text. Again, you need some kind of supervision for this. Summarization, I mentioned this already. Oh yeah, sentence summarization, no, there's sentence compression in a way, machine translation, and so on. So when we have, really strictly speaking, an input sequence, like an audio or in text, we talk about a sequence-to-sequence model. And for image capturing, that would be just a general encoder-decoder architecture. Now, I'm not gonna go into great detail about the background of machine translation, but I just want to explain a little bit motivate things, because it's also worthwhile to remember that the original transformer architecture was actually introduced for the purpose of machine translation. So the very first, it's not entirely true. The second paper on neural machine translation by Ilya Sutskever, so now OpenAI, as you all know, was also that they treated the machine translation as a sequence modeling problem. So back then they used LSTM, but for the purpose of this illustration, it doesn't matter whether it's LSTM or a different architecture. And so here the point was that we had an input sequence. So this is now very schematic. So we have an input sequence ABC, and we have a desired output sequence WXYZ. Right? So blue is everything that goes through the input, so i.e. the encoder. Then we have a separating token, in this case here, end of sentence or EOS, or end of sequence. And then we have, so these are two different LSTMs, one with parameters blue and one with parameters red. And, but they're trained jointly. And so what we do is when we train these kind of models, this sequence of pairs of sequences, so A, B, C, W, X, Y, Z, come in. And everything we see on the right now in red is basically decoding task, next word prediction task. Right? And on the encoder side, there's no predictions whatsoever. So the only purpose of the encoder is to aggregate information and feed it into the decoder. And that's actually also the important point, what I want to make here is that the connection between the encoder and the decoder forms a bottleneck, because we basically only have one transition from after C that feeds now into the decoder. And in the case of the LSTM, how do we do this? Typically, LSTMs also require an initial state, and it just means that the final state of the encoder is copied into the initial state of the decoder. But this forms a bottleneck because we have things now that we will issues with longer sequences to remember what was actually represented in A. So we have these kind of issues. And that was the motivation for attention mechanism, basically, right? So this, and there were some other fixes around this, including the Sutskever paper itself. They're quite hacky, so I'm not going to mention them here. But that was really also conceptually a bottleneck. How do we connect these two? Yeah, here I actually mentioned how, but let's not do this. So that then shortly after that led to the introduction of the attention mechanism. So that again was in a paper by Badano and colleagues, and also for the purposes of machine translation. That's actually not entirely true. Apparently, there's an older work by Alex Fraser on this for handwriting recognition, but this was like the paper that put the attention mechanism on the map. So, and is also used in image captioning in this paper, but mostly on machine translation. I should also say that this is very much related, so attention mechanism very much related to neural memory networks. So the basic idea of attention mechanism now, or using the attention mechanism in machine translation, is that we don't try to learn one global representation with a source sentence. So for instance, using the final state, hidden state of the encoder. But instead, what we try to do is we learn context-sensitive representations, or basically on a need-to-know basis, you would say. So whenever we are generating a target word, we look into our encoder representations and dynamically aggregate information with respect to our current information need. So it's a fairly dynamic process of aggregating this information. And so that's very similar to word alignment, but it doesn't really matter so much here. Where you basically have like word-to-word correspondences. And so the attention mechanism here that I'm talking about is cross attention, which later on we will also generalize to, well, generalize, also then transfer to self-attention. And this is also similar to word alignments, which basically you could see a bit like a dictionary-based approach, except that it's of course a shorter approach. So here's now how attention mechanism, or a way to let's say describe attention mechanism. So for attention mechanism, we have three components. We have a query, a key, and a value. We don't necessarily have to distinguish between keys and values, but for general purposes, now we do. So the query is basically all information. And that could be, for instance, at a certain decoding time step, we have an information. Keys is information that is already present. Typically, information in the decoder, in the encoder. So all the different keys that you see now here could, for instance, typically do correspond to word positions on the source side. First word, second word, third word. I'm leaving subword segmentation here. Just leave this out. And so now the query basically looks which of these input representations is most relevant. And of course, it's not an argmax decision. So for each of them, it measures a certain similarity. And based on that, it makes a weighted, it builds a weighted average of these. So what you see here, for instance, with the P1 to Pn, so this is our probability distribution over the different input positions. These are summed up, and so it's a weighted sum, and that results in a new representation built. And so the problem is, I'm slightly colorblind. I have no idea what the point is. I get this. So the thing up there is the context representation, which is the result of the weighted. So this now basically, depending on the query, so the same input can be different at each time, right? If we have a different query, we will have a new, what's often called a context vector, a new weighted summation. So here's just in terms of like an equation now. So the context vector C is just the sum over the similarities, but the similarities now assumed to be probability distribution. Okay. How do we define the similarity? So in the older paper, there were two alternatives. They actually used a feed-forward network, which I'll have listed here, but we're not going to talk about this now. These days, typically, we just use the inner product. So that's the dot product of the query and the key. We also can use a feed-forward network, but important thing is that these networks, these similarities, whether it's now an inner product or let's say a network that predicts a scalar value, these can be arbitrary values. So we want to make sure that they are resulting in a probability distribution. So we just run a softmax over those, over the input sequence. I should mention already, keys and values can be identical. So you don't have to use different values, although these days typically we do. All right, okay, that's. Yeah, an important thing here, of course, is that is really better. The main, let's say, benefit from attention comes from is that the entire computation is fully differentiable. So we can train the system end to end, and so that's really where the benefits are. So we can learn what is important at each time step, right? So that was really like a major advantage over other more hacky approaches. So now we can just train the whole thing in one go. Now, yeah, if we, for instance, do it in NMT, what is the query? So it's the current state of the decoder, right? What are the keys? And these are the representations of all the source programs from a certain layer. Typically, it's a top layer, but it doesn't have to be. And what are the values? It's a projection of those keys. Okay. And C is, as I mentioned already, like a weighted sum over the input sequence. It's often called the context vector. So how do we integrate those kind of things? Again, this is just a very schematic way of doing this. So what we have here on the left-hand side, this stuff here. So this is our encoder representation. Here we have now a decoder sequence. No, there's no initialization here anymore. So this is cut basically. Here we have a certain decoder state with a hidden layer representation. We use this to compute a similarity over the input sequence. That results in a context vector, which is somehow incorporated. Add it up. You can also put like a new concatenation in there or some other linear projection. into the final prediction. And of course, we repeat this for all of the time steps. And the context vector for each of the time steps will be different. So this attention has not only led to quite substantial improvements in translation quality, particularly for longer sequences. So, because you imagine you have a very long sequence and you have to squeeze everything into one fixed site representation, it's going to be difficult. Particularly if you have a task, if it's like a sentiment analysis task where you just have to predict one label, it's probably not so difficult to squeeze everything into one fixed representation. However, if you have to generate an entire sequence that fully corresponds to the input sequence, then this compression becomes more and more coarse-grained, and you lose more and more information. So that's why it was more particularly beneficial for longer source sequences. It can with complex mappings, and it also it can be useful for visualization. I have just a simple example here. So here's now an example from an encoder-decoder architecture, so machine translation. What you see on the left-hand side here is the on the y-axis here is the pointer again. Can you look? Is the source sentence on the x-axis is the output sequence, and each time that you see which words correspond to the word that we're about to generate. And if you look at this, it looks very much like these are actually they make sense. So these are fairly good word correspondences. Sometimes a bit off, but by and large, it's pretty good representation. Now, I should say this, of course, is for single-headed attention, right? Once you go to multi-headed attention, things become a bit more messy. So the interpretability of those things, yeah, it's a bit, yeah, it's trickier. Okay, so this is just for the attention vector. Before we talk about the transformer architecture, I also want to talk a little bit about if we have such a language model. So what we learned now is, given an input sequence, how can we predict what should be the output sequence? But right now, we just trained the model, which means we just can only say what's the probability of a certain output sequence given an input sequence. But we have to be given an output sequence. We cannot actually generate an output sequence. And for doing that, we also need some mechanism for doing these things at inference time, right? So I just want to introduce a bit here the beam decoding architecture. So this, again, we also use the term decoder here, which is a bit fortunate. So beam decoding, so as I'm always saying, beam decoding because inference time, where decoding is basically a model component that we also use during training. So in beam decoding, we assume that we have a trained model that basically has learned the mapping from input to output sequences, but now we want to apply it. So that's basically the same, right? If you use any kind of language model, you interact with it, for instance, through a prompt, what is returned is the result of beam decoding. And what we want to do is at each given time step, so we have an input representation Z in our case here, and also a target sequence that has been generated so far, xt. What is the probability of the next output word, right? And so this, of course, is now the actual true output, right? During training, what happens is what the model actually, let's say, were to predict and what it observes during training can differ. But for the next time step during training, it doesn't matter, right? Even if the model makes a wrong prediction, it still gets the correct input as the correct output as the next input. At inference time, that's of course not the case because we don't know what the correct output is. We generate a word and we just assume that's correct, and that becomes the input for the next time step and so on. So that's why sometimes things can also really go off attention, right? If you start generating wrong output, it basically reinforces itself to generate more wrong output. So this is so for instance, in machine translation, that can sometimes happen that you translate into the wrong language. Right? You translate into a language, and then it starts one or two words are in the wrong language, and then from then on it just assumes, oh, I should translate it into French, and it continues into French because it kind of starts believing its own predictions. But that's all it has, of course, to go by. Now, of course, so during training, we basically know what the true output is, and therefore we use it as a next input. but at beam inference, beam decoding, we don't. So we actually have to select it. For instance, through an argmax operation, right? An argmax 1, or it can be also multiple argmaxes. So let me just do this. And oh yeah, I should also say, so I'm explaining this now in the context of machine translation, but it's the same. It's the same whether for image capturing or for summarization or for dialogue systems. Beam decoding is basically the same architecture that you use. So if you have a beam decoder, it's versatile, right? You can apply to any kind of sequence-to-sequence problem. Okay, so now I'm just going to explain a little bit by example. So what we have is, so I'm now talking about states that we have in our model. So the initial, we also have an initial state, and the initial state is just, we have an input representation through the encoder, and we know that we now want to start a new output sequence that we have with this ESSIR. Pointer again, focus. Okay, we have an input sequence S, start that, and we now have also our model has a number of top predictions. Of course, it has thousands, tens of thousands of predictions. Here I'm just focusing on the top 4. So these are the top 4 predictions that the model wants to make at this point. It, this, that, and these. These are the top 4. With the corresponding log probabilities. And of course, below that are many, many more with lower probabilities. Now we take, oh yeah, let's also assume that we have a beam size of 3. So in each point in time, we consider 3 hypotheses for further expansion. That's basically what beam size 3 means here. So we take these 3, and now we feed these 3 as potential inputs for the next time step. So the first one, it, this, that. So that now leads to branching of that tree. So now, with it as a continuation, now we have new top 3 predictions. So we are in a new state. Now is, was, has, will are the top 4 predictions. For continuation of this, so the second branch, we have 4 different types of predictions. Of course, there are many more below that, but these are the top 4. And similarly for that. So now what we do is, so now we don't expand out again each of these branches into 3, because then the whole thing would become exponential. So instead, what we do is we now look for this time set 1, across all of the candidates. So in this case, we have 12 candidates, which include duplicates. Right, so for instance, I don't know, is a hypothesis of the first and also the second state, and of the third state actually. So anyway, we have these 12 candidates, 3 times 4. And we look at the top 3 of this, the top different 3. So in this case, so what are the 3 with the highest probability? Is, has, and another is, and all the rest is lower. So for instance, the top one of the third state, which is has, so that has a lower probability, so it's not even making the lower top 3. So these are now the top 3 candidates that we have. And that also means that the last state does not contribute to any of the top 3 candidates. So that does not contribute, so that basically gets pruned out. We ignore that. We only expand the other 2. So in this case, the second one has 2 states in it, right? So has is, and the first one is, and we continue with that. And note, so the probabilities now are also now the probabilities of the entire sequence. So if you follow that path, right? So if for instance, full stop minus 2.27 is the probability of it is full stop given the source sequence. And so on. So we basically continue this, and continue, and continue, and continue. And until when? Until the whole thing stops. So we have to have some kind of stopping criterion. And typically, there are 2 types of stopping criterion that we have. So the first stopping criterion is what we see here, is once our model wants to generate the end of sequence representation. So this is the /s. So once our model thinks like, oh, this output sequence should be finished now, that's when we write back a hypothesis. So we basically follow the path. So in this case, we would write it down, this is in the end of sequence. And there's another one further up. So that's one way of writing down candidates, and the other, but there's no guarantee that this will now lead to any kind of termination. So we also have to have a bit of a harder criterion, which says after a certain number of time steps, we just stop, and then we don't generate. But note, so that if we go through time, at each given time, only 3 hypotheses are active. That's where the fixed beam size comes. And once we are at the end of this, we look at all of the candidates, we normalize their probabilities. When, not sure, do I have this? Yeah. So we also have now all the candidates that we have in there. And the most likely one now from this list is returned. And typically it's in this list either if it has like end of sentence or end of sequence as a generation, last generation step, or if the length is up to a certain, let's say, threshold. And then what we also do is we normalize them by length. Because otherwise what would happen is that longer sequences always have a lower probability than shorter sequences, and that would give shorter sequence an unfair, let's say, or undesirable benefit. So therefore, we always normalize by the length of the sequence. And then what we return is after that, we return the one argmax of the sequence. And basically every time you interact with a model, right, you use a machine translation system, or whether you use a large language model, it goes through beam decoding. And beam decoding, I could also say, is a bit more time-consuming than training, because there's a bit more interaction between CPU and GPU. So it's not that everything is fixed. So during training, you can push everything to the GPU. Here it's a little bit more time step one, because you have to also select the top candidates, you have to make choices, you have to maybe rearrange, like it's a bit more bookkeeping involved here. So that's typically why beam decoding is also considerably slower than training these kind of models. All right, so again, so this is just beam decoding in a nutshell, but it's the same for all of the models that we use. And oh yeah, I don't have this in here. So you may want to, so here I gave a beam size of 3. So one would think like the bigger the beam size, the better the output actually. But oddly enough, that's not the case. So these models, if most of our state-of-the-art models have a beam size of 5, maybe 10, so it's not very big. And often what happens is if you use a larger beam size, more noise sneaks in, and often performance drops. So it also tells us that the way in which we explore the search space is really not optimal here. And also, another thing to mention is that you would think, so for instance, with the beam size, larger beam size, you also get a bunch of candidates at the end. So that gives you some variation in the output, right? So you could, this for translation, there's not only one way to translate it, there's not only one way to translate a sentence, right? There are many alternatives that may be equally good, but different. And that you also see quite a bit of variation in the beam. That actually is somewhat disappointing. So there's often very little variation in the beam. So if you really look for, let's say, different alternatives inside of the beam that really are different paraphrases, the degree to which they're paraphrased is very little. They're very close to each other. So that's just there's a whole bunch of like entire research line on like variation and increasing the variation during the beam decoding. Right. So that's just for the beam decoding bit. Now let's slowly transition into the transformer models. So self-attention is the mechanism is exactly the same as cross-attention that I talked about before. And unlike whereas the attention mechanism, the cross-attention mechanism between encoder and decoder was really a way to connect two model components, whether they are RNNs, or when I talk about RNNs, like RNNs, LSTMs, something like that, or whether they're CNNs. But in self-attention, it's now a way to make this replace the recurrent aspect or the convolutional aspect of a model. So this is now really a way of aggregating information within a sequence itself, not between sequences, like the encoder-decoder sequences, but in the sequence itself, right? And so the older models, so for instance, here we have a recurrent model, multi-stack encoder model, is so they knew that there was like this left to right. They ideally would like to incorporate information from both directions. There are many ways around bidirectional LSTMs and so on. And so the nice thing for self-attention, so this is now encoder-based representation of this, is that it basically just looks left to right directly, right? So it's bidirectional by design. And it aggregates information from both directions. Of course, the decoding, we have to do some masking there, but for the encoder, we can treat it like this. And so it's very similar to the cross-attention, like the way we use the model. So if, for instance, we have an encoder here, and it's the same for the decoder, that's right. So for each of the time steps, we have a, here I just now have a query and a key. So I omitted the query. Sorry, I omitted the value. So we have a query and a key. And for each of these time steps, I pick one now randomly because everything happens in parallel. So I use it for all of the time steps. So one of the time steps, we now compute the similarity between this query and all of these keys, right? And then this gives us a new context representation. So basically it means now, given this word, what other relevant information is relevant from the words surrounding it. And for good measure, we also combine that with the original embedding itself, or later on layers with the output of the previous layer through a residual connection. That we also a feed-forward layer, again residual connection, and so on. And we do this in parallel for all of them. So this can happen fully parallel, so it means also it happens independently of each other, right? So there are also some computation advantages here, so we don't have to do it in a time step sequence, but it can be pushed through in one go. And this is our first layer, and we repeat the same for the second layer, and so on and so on. So first thing is, so why do we need these residual connections? I mean, so residual connections originally were introduced to help with gradient flow, right? And they also help here with gradient flow, but they also have another side effect. So because if we didn't have residual connections, it became an information soup. So each of the time step aggregates information from other time steps, but there's no guarantee in a way that any of this here has any correspondence to this time step, right? Because information flows back and forth. So by having the residual connection, we kind of anchor this representation to this time step. So we make sure that each of these time steps also is well represented, because otherwise it could be that this time step here aggregates all of the information from here, nothing from there, and here. So basically everything can be smeared out, right? It becomes like a soup of flowing information. So by having these residual connections, it allows us to anchor. The other way around it, you could also have, let's say, a attention distribution, make sure that half of the attention distribution is to the current time steps. There are other ways around it, but I'm just saying, like, the residual connection has this two aspects, right? Gradient flow, but also the anchoring with the current time step. Right. So the feed forward layer I mentioned before already is also applied pointwise. So the weights are shared for each of the time steps. And it's just an MRP, right? Where, for instance, we take the context vector from a layer from the previous time step as input. We have a linear projection of that. We also have a bias term. We go whole thing passes through a rectified linear unit, a ray loop, and then again we have a linear projection on top of that. Oh yeah, followed by for a dropout mask. Okay. We also, in addition to the residual connections, we also use a layer norm. So that's again another way of stabilizing the training process. So the layer norm is also applied in this case to the context representation after we have applied dropout. And let me just go through an example of what the layer norm does. And so the point of the layer norm is that it normalizes our activation. So if we train a network that has multiple layers, it can happen that the activations vary greatly between layers. So we have to normalize things and bring them roughly into the same distribution of values. And in computer vision, a few years before Transformer was introduced, there was also a technique called batch normalization that used this. And so the point here is that we normalize our activations by the mean of the variance. And the layer normalization is very similar to batch normalization, based on the same mechanics. It's just how we normalize, which values we take as normalization varies. And probably the best way to describe this is, I forget about this, is to look at an example. So this is now, what the first thing we see is the batch normalization. So we have as an input batch here with 4 instances in it, and our hidden layer here has 8 units, right? So very small dimension. When we do the batch normalization, we look for a given unit, neuron, always slightly allergic to the term neuron, but anyway, for a given activation, we look at all the values across the batch. Then we compute the mean on that, compute the variance on that, and we use this now to renormalize everything. That gives us a batch normalized value. So for computer vision, that's actually quite okay to do, because in computer vision, there's one thing, namely that all of the inputs typically are of the same size. So all images are 120 by 128 pixels, or can easily be made into 128 by 128 pixels. In language, that's not really the case, right? Some senses have 20 volts, other senses have 40 volts, and so on. So that means also that our batches typically will vary in size. And so that's why batch normalization really never made it for NLP tasks. But there's a very simple way around it, and that is to use layer normalization. So here what we do is, instead of using across the batch, the different instances of the batch, we normalize across all the activations for a given instance in the batch. Right? So for instance, if a model has, in this case, dimensionality of 8, it will always have 8, so that won't change, right? So then for a given batch, instance, you go, in this case, down the column, you compute the mean, you compute the variance, and we use that then to renormalize our values. And so that's what we do layer normalization. And again, layer normalization is quite useful, because it really helps to tame these models a bit, to make sure that they are, during training, and I'll come back to that, are somewhat well behaved. Because training transformer models is still a bit tricky. So you have to be a bit careful, because they can really go off the rails quite easily. All right, so this is for the activation normalization. I think I'm going to quickly talk about positional encoding, and then take a 5-minute break, at least. No, let's take a 5-minute break now, and then let's do the yeah, because otherwise I hasten too much to it. Let's do a 5-minute break now, and I'll see you at 20 past. Right, positional encoding or positional information. Now, when we in a transformer architecture, I should say, self-attention architecture, all of the information is processed in parallel. So each of the positions is just we just put it to. Unlike in a SCM, for instance, where we have really sequential nature, where we go one time step, another time step, and the next time step, and so on. This is not the case for self-attention models. And that also means that all kind of the sequential nature is gone. Everything is now a bag of words, basically, bag of tokens. So we have to get that sequential aspect somehow explicitly into the model. So for LSTMs, that's inherent in the way the models are trained, but not for self-attention now. So we have to get this in there. So we have to distinguish between these different positions, because otherwise the model itself will not be able to make that distinction. So we have to encode this information separately for each of the input tokens. And so there are two strategies for this. So one is that we learn the additional embedding, just like we learned in board embedding, we learn positional embedding randomly, or randomly initialized, and then we train it. So we learn an embedding for position 1, for position 2, and so on. Or we use what's proposed in the so that's for position, and then we learn this. Basically, we can also learn this, right? So the criticism of this was that it only works for embeddings for positions that we have seen during training, and it doesn't generalize to unseen positions so much. Okay. And if we learn such an embedding, so then what we do is just combine it with our next word. We just, for instance, add them up. We could also concatenate them, but typically we just add them up. The alternative approach, and that by the way works quite well. So also people have used this prior to the transformer paper for CNNs. which of course have similar issues, because CNNs also are not sequential in nature. So they also have to have positional encodings in there, and so work by back in the day Facebook, where they also use CNNs for sequential models. They used positional encodings just like this, or position embeddings, I should say, where they learn them. The alternative is, and that's what's proposed in the transformer paper, is that we actually have we have a function that we don't have to learn, encode the positional information. So there are no learnable parameters, and the claim is that it generalizes better beyond training. There's a bit of a question mark, but that's really the case, but that's another story. And so one of these requirements is also that this function should have somehow an upper and lower bound. And one way of doing this, and that's the way proposed in the paper, is to use sinusoids. So it's a bit out of that, but basically what we use is for each of our dimensions in the model. So for the embedding dimension, so all of them, if we have a model size 512, for each of them, we learn a sinus or a sine or cosine function. No, not we learn, sorry, we introduce a sine or cosine function. And they differ, each of the positions, now whether it's for in the model position 1 or model position 2 and so on, both of the weights, so the sine and the cosine weights, they differ in terms of their wavelengths, basically. And we have them alternate between sine and cosine, and all of them with different lengths. So best way to do this actually is to visualize this. So what we see here is so now different than from the original paper. So the original paper, sine and cosine are interleaved. So dimension 1 is cosine, dimension 1 is sine, dimension 2 is cosine, and so on. Here we have like the first one. Is model size 512? I think it's model 512. First 256 are all the sines, the second one are all the cosines together. So it makes it a bit easier to visualize, otherwise it's like one big mess. And what you can see here on the y-axis, you see the different positions. So position 1, position 2, and so on. And if we now, you can also quite easily see how this generalizes to positions that we haven't seen during training. How it also can then, the unseen positions can relate to positions that we can see. And this is basically now a way to just have a fixed function that we don't have to learn for all the different positions. All right. And again, similar to the embeddings, position embeddings that we also learn, we have this as a embedding that, for instance, add to the word embedding, which we actually learned from the during training. Right, so this is, but we do need this. So without any kind of positional encoding, everything becomes basically, again, a bag of word soup. So we lose all of the sequential components. Another thing that is also very, let's say, the core of transformers is the multi-headed attention. And there is really not so much to it. It's very much like any kind of attention mechanism, except that we have multiple attention mechanisms in parallel. And basically, what it kind of allows the model is to say, well, with this head, it allows different heads to have different functionalities. So for instance, it could be that different keys are equally relevant, but if I only have one head, then I either have to have, let's say, uniform distribution or like a bimodal distribution. If I have multiple heads, then I can pay one head to pay attention to these kind of aspects, another head to pay attention to other kinds of aspects. So for instance, one head would function, let's say, as a more like semantic aspects, and another head more syntactic aspects. Again, without now not really going in great detail through the technicalities, but what we do is, so we have, it's very similar to what we had before. We have our queries, we have our keys, we have our values, except now for each of the heads, we have a different projection, and in particular, it's a down projection. So if we have a certain model size of D, then we now project them down to a smaller size, namely D divided by the number of heads. And then for each of the heads, we compute our attention distribution and then use that to compute also a context vector for each of the heads, and then combine them again through, for instance, a concatenation. So here so D is now the size of the per head, and it's basically the model size M, sorry about that, divided by the number of heads. And as I said before, for each of the heads, we just compute this in parallel. Now, one should also say, so while in the paper, it's a bit hand-wavy claim that allows them to model to focus on different aspects of the fluency or topicality or semantic. It's a bit, I would take this with a grain of salt. I mean, multi-headed attention definitely has some benefits in terms of performance. It gives a bit of an edge. But it's very difficult to say really whether they focus on completely different things. It basically introduces a little bit maybe of redundancy into the model and also gives it a bit more flexibility. But of course, it's not really that you have like fully expert attention heads like one aspect, another completely different aspect. So it's all quite a bit of overlap here. But it outperforms simple attention. Or simple-headed attention. How many heads you need? Yeah, it's a bit of an experimental hyperpart. Okay, so and so all the components that we have seen so far, like the self-attention, the positional encoding, the layer normalization, so is exactly the same that we use in the decoder architecture. So the decoder component of the encoder-decoder architecture is very similar to the encoder architecture, except that we also have to integrate our decoder and encoder attentions, so cross attention, like we have seen at the beginning, and that self-attention has to be limited to previous time steps. So that's of course also the same for decoder-only models. Right, when we compute self-attention, you can only look at steps or aggregate information from previous time steps. Because if you look to the future, then during training, your prediction will be trivial, right? Because you know already what the future is, and your model basically doesn't learn anything, right? You get a loss of zero, and it's pointless. And of course, that's also not how it will work later on, right? When you use it at inference time, it doesn't know what the next output symbol will be. So again, here, schematically for encoder-decoder architecture, so things are very similar, except that we now have our self-attention here is masked to the right. To the future is masked. So each time step we can only look at the time step itself and to its past. When we train these models, basically, I should say we actually train them as if there was full self-attention, but then we just mask out the results. We just need to push everything. Then in the sublayer, we also aggregate some cross-attention information from the encoder before, and then we go to the next layer and so on. Continue. So very similar, right? So again, here we have our self-attention, decoder side. We combine that with the cross-attention, and then we also have a feed forward again in there, and that computes or finishes our first layer, and we continue with the second layer, and so on up to the top. So very similar to the encoder, except for that we now also have the cross-attention. Now, when we train these models, there are also some practical one should bear in mind. So if you train a transformer, it's not, things can actually go wrong quite quickly. So there are a number of things one should observe. So there are a number of best practices, let me say, that are useful when we train a transformer model. So firstly, batch size matters. So by and large, a larger batch size, and also how do you define batch size? So here, nowadays, we typically define batch size a number of tokens, but not so much a number of sequences or sentences. So a larger batch size is by and large preferred because it aggregates the gradients over a larger number of samples, and therefore also is less susceptible to outliers and therefore a bit more stable. However, if you have a very small training set, so if you're in a kind of a low resource scenario or in a fine-tuning scenario, then a large batch size is not such a good idea, because it basically just uses a few batches to go over the entire training data, and therefore also is very likely to basically not fit the model. But for training on the larger corpus, a large batch size is preferable. Learning rate. So also for the learning rate, so in this paper they also use the this paper, like the self-attention OED paper, or attention OED paper. They also use the learning rate schedule with an increasing decreasing rate. So this has a number of components, the learning rate, which I'm going to show actually in the next. This is probably the best way to illustrate this. So what you see here on the y-axis is the learning rate, and what you see on the x-axis is time, like updates basically. So it has a warm-up phase during which the learning rate will increase up to a point, and after that we basically have a slow decrease, reciprocal. So what it allows us, the model, is to move away from potentially poor initializations quite quickly by increasing the learning rate over time, up to typically 4,000, 8,000 updates. And from there on, then we go slowly, we go down. So also bear that in mind. For instance, if during fine tuning, one has to really know where in the roughly where was the learning rate at the end of the pre-training, because that can be beneficial if you want to continue with fine tuning. Because I think fine tuning with the warm-up phase, I would be careful with that, because then you kind of like move away quite quickly from what the model has already learned. You may move away too quickly. So you have to be a bit careful how you set the learning rate, and also how you set your learning rate regime when you do the fine tune. Right, okay, so until it reaches a certain maximum. All right, okay. So even though you could say like, okay, so we move quite aggressively and move away from the initialization, the right initialization still matters. And so Xavier uniform initialization is a commonly used one here for transformer models. So this is just really something to bear in mind. So batch size definitely, of course. Yeah, no, batch size learning rate, I would, particularly if you do the fine tuning, check out how the model was trained and how big your fine tuning data is, because that really can have an impact on the performance later on. Okay, so this is for the transformer training of the transformer. So this is really now using transformer for an end-to-end task, right? So with treatment state, summarization, and so on. But quite often we also use transformers nowadays as a an intermediate thing, right? So it's we use the representations for other tasks. And in the a long time ago, so we used basically when we talk about representations, we talk about representations like static representation, maybe like word embeddings, for instance, right? And these are, of course, also a byproduct of an actual task, and also transformer models still use word embeddings, right? But what we also know, of course, is that these word embeddings, they're the result of a very shallow network, right? So they're very close to the input, but we want to use actually also deeper representations for this. And ideally, we want to use also the whole sentence context to get better word representations, contextualized representations. Now, again, many years ago, we used word-to-vec models, for instance, to learn these kind of word embeddings, which had a very limited context window, just a few words left and right. And these embeddings were static, of course. It was one embedding for a word, regardless of its occurrence, of its context, right? If you have a word like he took the train to Munich, right? Train has one embedding. She had to train for her next match, would have the same embedding. Of course, we have static embedding, right? He interrupted her train of thoughts, right? Again, same embedding. So this embedding has to cater for these different meetings now. And that's, of course, undesirable. And that's why we want to have some kind of like contextualized models for this. Now, let's say we have a deeper network. This is our multi-layer. It doesn't really matter. Could have been as well like a transformer. It doesn't really matter. It's a complex network over entire sequence, over multiple time steps. The question is like, which representation do we want, right? If we have, let's say, word embeddings, so word embeddings live down here. It's the same for all occurrences of training. Even in a deeper network. But maybe we also want to use this as a contextualized representation, or this, higher up in the model. These are our choices. Another choice for our representation is, or what kind of representations we get is, in addition to the, let's say, depth in the network, how do we train the network? Is it, for instance, trained in the next word prediction? Or is it trained in a sequence classification task? Because both of these tasks will result in different representations. So, for instance, I can imagine that something like a next word prediction class will have much more, let's say, lexical information encoded in a given for a given word than let's say a sequence classification task. Because for the sequence classification task, it probably doesn't even know exactly what the lexical meaning of this word was, just roughly what is its purpose for this classification. Right? So this is also something to bear in mind. So how you train these models to get these representations matters. And so what you want to do is, in order to get like good representations in deeper networks, is you want to integrate sufficient context, so you can distinguish between different meanings of words in different contexts, but also not capture maybe too much, so that it kind of washes out, particularly if your task is, let's say, overly general. So you choose the right layer and you choose the right task. And when we use these kind of like pre-trained models, so the task that we use typically is a model like, let's say, a sequence model, LSTM or transformer. And then the task itself is a general task, which doesn't have to be a sequence task, right? It can be also a classification task, it can be a question answering task, and so on. But the important thing is for the pre-training task, it should be a task for which we have large amounts of data. Later on, for the classification task or for the fine-tuning task, it can be relatively small data. But for this pre-training phase, we really need a large amount of data. And that also has certain restrictions on the type of data that we can use. So for instance, annotated data, human labeled data, is a bit problematic because we often don't have huge amounts of that. And so therefore that's why tasks such as word prediction and next word prediction and language modeling is such a suitable task, because that's we get for free, basically. We train the model on this general task. We update our parameter, and then doing fine-tuning, we actually use this pre-trained model and connect it, well, to an actual task. And that could mean that we use either these parameters from the general task as an initialization for this task, or maybe we even glue together different architectures. So there are several ways in which you can do this. But again, for the fine-tuning task, that typically involves a supervised signal, unless you maybe do something, let's say, like a domain shift task. And you can combine then the pre-trained model and the fine-tuned, you can combine these into, let's say, a common model. Right. And the most prominent example of that is BERT, of course. So BERT is a very simple model. It's just the encoder component of the transformer architecture. And it has a pre-training and a fine-tuning phase. And what happens during the pre-training phase is that we just train a simple word prediction task. Unlike a decoder-only model where we predict the next word, now we just mask out words that we want to predict in the context. And of course, that's an easy task because it doesn't need any kind of supervision. We just use text, we withhold some information, and then the model has to predict that the information that has been withheld. For the fine-tuning then, of course, we use it on an actual supervised setting. Okay, this is a bit crossed out here. Right. Okay. So if we do for the encoding, so so the original BERT actually had two tasks: the prediction task, which I just mentioned, and also a sentence prediction task, namely if the next sentence predict. The sentence prediction task these days we don't really use anymore because it turned out just to be too simple of a task. So you just have to predict whether the next sentence in the training data was actually the next sentence, or whether it was noisy sentence that was deliberately put there in the training phase. But the model basically has like a 99.5% accuracy on this, so it's not a very useful task. So models like Roberta, for instance, don't include that task. Now, when we do the training, we mask our input. And that means like random positions in the input are withheld. So just we put in a mask symbol. And so for 15% of the input tokens that is masked, in 80% of those cases, we actually put in a mask token. For 10%, we put in a random word. And for 10%, we put in the original word. So why do we also have to put in the original word? Because later at inference time, the model will never see any mask. Right. So the model should not only think like, oh yeah, I only have to predict anything if there's a mask token. So it's important for the model also to know that the actual words can occur there. And the random word is just to introduce a bit more robustness, maybe that for instance there could also be error in the input. And then the loss is only computed for those masked positions. For the other positions, well, we also compute it basically, but then later on we just zero everything out except for the masked positions. So the gradients are only accumulated for the masked positions where we have withheld and make an actual prediction, let's say. Right. Now, when we use this, I haven't really talked about BPE. So BPE or sentence piece is a subword segmentation, right, where we break words into smaller parts. So the original word worked at the BPE subword level, which means subwords have been withheld. So if we have full words, so for instance, like the developers mask the property. So the question is, what could the word be that we have withheld here? And you could think of many words like, I don't know, bought, reviewed, I don't know, assigned, whatever, right? But if we apply BPE or sentence piece, this task can become, we also now apply this at the BPE level, right? So not at the whole word anymore. So we have something like the developers, then ed, the property. So we know already, okay, it's a verb past tense, most likely, because it ends in ed. But the problem is, so for some BPE segments, the task now becomes very easy. Right? If I have so developers view the property, it's pretty clear what that mask should be, namely ed. Right? Nothing else really makes sense. Yeah. And so some of these masks are basically less useful than others. So that's why also later on the variation of this, where basically whenever they're masked at the whole word level. That means all BPE sub-segments are masked, and then all of them have to be predicted. So in order to really learn the lexical information, because here by just learning the ED, it's basically a trivial task. Okay, so here's another example, right? Instead of like having view or ED masked, now we have to mask and therefore to predict both of the words, and that gives us some improvements. All right. But so that's for BERT. So BERT is basically just the encoder of the transformer architecture. So the last model I just want to talk about is also an encoder decoder, but now as a pre-training setup. So transformer itself was not really meant for pre-training, was really properly input sequence, output sequence, so required human annotation, namely in our case, machine translation parallel data, human translated data. And we cannot just give it English data. So if we just give it English data as an input and English data as an output, and if we train a model on that, the model basically just learns how to copy. So it doesn't learn anything useful. So we have to really think a bit about, like, if we want to use an encoder decoder, how can we do this, right? So again, reminding ourselves what BERT does. BERT, we withhold some information and we have to predict this information. A model like GPT, the decoder-only model, is in a way also similar to BERT, except that we now always predict the next tone. So our mask is basically always the next tone that we have to predict. It means also that it doesn't make any use of the future to predict the next tone. But so what about tasks that require an encoder and a decoder? Right? How do we pre-train those? So here BART, people are so innovative with their names. So BART now was a variant of that is now an encoder-decoder model. And importantly, just like BERT, it's also a denoising model. Maybe we give it some noisy input, the model has to now come up with a correct input. So it also consists of a bidirectional encoder. It doesn't have to be bidirectional, but anyway, it has to consist of an encoder and then also a normal autoregressive decoder, so a normal left to right prediction decoder. And BART has a number of noise functions. So, for instance, it has the token masking, which is very similar to the BERT. So we know that there is a word in the second position and in the fifth position. There was a token there, and we have to predict that token. Right? So the underscore means there is a token, we have to predict it. And so the desired output sequence is what you see below, right? ABC.DE. There's also a sentence permutation task. So again, in comes a document, so a number of sequences, a number of sentences, and then they are shuffled around. So we don't do any permutation within a sentence. So it's not like the words are. Document rotation, where just a word from the beginning is like copied, or so a sentence from the beginning is copied to the end. So we also have token deletion, which is slightly different from the token masking. So now we delete a word, but we don't tell the model. So basically, it's just withheld. And the model then has to figure itself out. Oh, actually, there should be another word in here that was not given as a which is different from token masking. So here the model knows, like, here's information that has been held. For token deletion, it has to figure it out itself. And for text in filling, so here's similar to token masking, except for we don't know how long this span is. So we just, there's some stuff missing here, and then the model itself has to figure out whether it's 1 word, 2 word, 5 word, like that. So it's a bit more like span in filling, maybe span. And so this is the BART model. And so this, of course, we can actually train, and so that's important thing about BART. So we can also train in monolith BART, in input-output sequence, namely where the input and output is the same sequence, except for we apply noise function to the input. So therefore, it means also we don't have any problems to get our hands on our data, because it does not require any kind of labeling. So everything we can just push in there, and it can be trained in a self-supervised fashion. Oh yeah, here's just basically what I explained this. So you can these models, you can train them, so models like BART, you can use them for a bunch of tasks, like label classification task. So this is not a sequence classification task. Probably doesn't make so much sense actually to use an encoder-decoder model for that, but you can. You can also use it for span prediction. So for like question answering tasks. So span here would be like an answer span prediction, like squat, for instance. But you can also use it for actual encoder-decoder, so sequence to sequence tasks, like machine translation, where I have or where one has a pre-trained encoder and decoder model, so just in one language. But of course, this by itself does not suddenly able to translate. So it still has to be fine-tuned on an actual translation task. And typically we do this by, this is now a different way of using the fine-tuned and the pre-trained model. So not by, let's say, using the initialization of the pre-trained model, sorry, the output of the pre-trained model as an initialization for the fine-tuned, but instead here is we have a pre-trained model, and now we concatenate it with a randomly initialized model that is used during fine-tuning. So what we have here is we have a randomly initialized encoder, and the output of that now feeds directly into our pre-trained encoder. So in the original encoder-decoder pre-trained model, the word embeddings go in there, and now actually the output of our encoder that we just fine-tune, train during the fine-tuning phase feeds into this. So that's another way of combining, let's say, a pre-trained model and the fine-tuned model. And this is now one way to use this also for machine translation. Interesting enough, this performs really quite well, even though it is trained on not pre-trained directly on a translation task. It has a pretty good performance that definitely outperforms training the model only on the limited, let's say, fine-tuning data that you have for a given task. So that was actually quite a nice finding. Right. Okay, so that brings me basically to the end. So let's just recap a little bit what we've seen. So we have seen that talked in the first part about sequence-to-sequence models, the encoder-decoder architecture, also the attention mechanism, right? The context now of cross-attention there, and also beam decoding. How do we use these models during actual inference time? How do we generate sequences? Then the transformer model, the layer components, the position encoding, self-attention, that's basically just a variant of general attention mechanism, and also the training of the model, right, with the learning rate and also some practices in terms of batch size. And then the last part about the contextualized representations, where we use models, for instance, get representations that can take meaning changes or say, behavioral changes of words in different contexts into account. Most commonly used encoder only model named BERT, but also you can use this for an encoder decoder pre-training model, just like BART. That is for about 5 minutes. Questions, if there are any. Yeah. Right. Okay, that brings me to the end. Thanks. Questions? Oh, no, that, yeah. Yeah, you're sitting next to the guy in front, and then you. Hey. Yeah.
Training of components to work with learning rates schedule. We will have like linear at the beginning and the this is kind of heuristic that people use, but do you have any intuition?
Oh.
Or is it just that people do that?
I mean, the decay that has been around for a long time, right? So this is basically what is new here is at least was new to me, maybe the optimization niche of machine learning. They used the warm-up phase before. I don't know that. The intuition here was that that I think the model is really quite okay. So I've heard through people that the people developing transformer had a hard time getting the model to train. So when they developed it and had an architecture together, it just would not train. It just would go all over the place. And one way to tame this was indeed to use this warm-up phase. And I guess the intuition was just that in the beginning it was just too, whatever initialization you picked was just too unreliable. It just, I don't know, would just stick in this local optimum, would not get itself out of it. Because during the warm-up phase, you allow the model to some extent to find a little bit roughly what is a good region fairly aggressively, and then go from there. Of course, there's no guarantee you get it for global optimum, but it gives the model a bit more of a chance to step out of whatever the initialization was. So that's again very hand-wavy, but the same could be said about residual connections, the placement of layer normalization, why above here and below is.
For machine translation, it makes a lot of sense that encoder and decoder architectures are very intuitive. Could you maybe give a bit of intuition why decoder-only models are suddenly popular for the text that we see a lot today?
Yeah. That's a good point. So there is both models have both encoder decoder model and decoder only model have certain advantages. So one advantage, let's say, if I have, I mean, you can have machine translation also in the decoder only model. There's no reason not, well, in principle, there's no problem with this. So for instance, if I have a source sentence like S1, S2, S3, S4, so these are the word positions total. And I also have a target sequence, 1, 2, 2, 3, different vector. If I have a decoder only model, that's a representation at some point here, I can only use this as a representation for S2 And then it would predict, running out of space here, it would predict S3, right? Because that's the next word for decoder only model. It cannot use any information from S4 or S3. Is it desirable to have this information? Maybe. I don't know. Right? It depends a little bit, right? In an encoder only, an encoder decoder model, you basically give it. So for instance, this was an image, maybe you actually would like to know what's in the bottom corner and not just read the image line by line. Right? But on the other hand, for a decoder only model, there's another advantage, namely an encoder decoder model. So this now has to predict D2. That means all the representations here are only with respect to the gradients that we get from making this prediction. There's nothing in itself that also says, well, what about the source sequence? There's no loss associated with the local source sequence itself, only with the purpose of this target sequence. Right? In a decoder only model, on the other hand, you also have a loss here. You maybe have a loss with respect to the next word, source word, but also with respect to the target word. That would be an advantage because, right? Because the other thing is, of course, the self-attention at some point also goes here. Right? So that's because the self-attention does not stop here. So that's another advantage of a decoder only model. There's one other advantage, but that's not really a difference between encoder and decoder per se, is that typically our encoder decoder models, the cross attention is only with respect to the top layer of the encoder, whereas in a decoder only model, you do it layer wise. So self-attention the first layer, self-attention second layer, you go with so. But we could also do that in encoder and decoder architecture. There's nothing that stops you with the test actually one page. But of course, this is the more general task, the decoder only, because in a, let's say, normal language modeling task, encoder decoder maybe don't make so much sense. Whereas for machine intelligence or summarization and so on, you have clearly this the input, this the design output. So decoder only, but so the decoder only models that are actually out there for machine translation, they don't perform as well as the encoder decoder. But it is the more general demonstration. All right. Any thoughts? Thank you.